What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles. In this video, I'm going to talk about conditional statements, which is a really important topic to understand. Really, if you're taking any kind of course that involves proofs, whether it's reading them, writing them, whatever it is, it's important to understand this idea of conditional statements. So this video is going to make a lot more sense if you have some basic knowledge, some basic understanding of propositional logic. So if you don't, then make sure to click this video. I'll link it right up there. I made an intro to propositional logic video that may help you understand this video better. But if you're ready and if you're excited, then let's go ahead and get into it. And this is really cool stuff. And the reason why is because we can start proving stuff once we understand this. Once we understand these conditional statements, we can get into doing direct proofs, proof by contraposition, proof by contradiction. I can make all kinds of fun videos on proofs, that's when it really gets fun. So first we got to get through this, the notations, the definitions, then we can get to the fun stuff, all right? So let P and Q be statements, then the statement P with this arrow from P to Q. This is the notation we use, okay? P with an arrow to Q is called a conditional statement. You may also hear it called an implication, okay? And what this means is, and how I personally read this out loud is as if P then Q. So when I see something like this, I read it out loud to myself as if P then Q. You may also hear a lot of different forms of this. You may hear P implies Q, which is why some people call it an implication. Q if P, Q whenever P, P only if Q, P is a sufficient condition for Q. There's all kinds of different stuff you may hear, okay? So refer to your textbook if you're taking a course. Refer to what your instructor wants you to know. But for me personally, when I read this out loud, I read this as if P, then Q. And what's cool is a lot of important theorems and important facts in math are of this form. If P, then Q, or Q whenever P. We see this come up a lot, and we'll get into that a little bit later. But first, P is called the premise. That's what I personally call it, but I've seen hypothesis, so I thought I'd put it in there. Q is called the conclusion, but I've also seen consequence, so I thought I'd put it in there as well. All right, guys, now we're going to look at the truth table for a conditional statement, and I do have some tips to help understand this a little better. Students tend to struggle, especially with these last two rows. So let's go ahead and look at these tips I have. First, think of an obligation or a contract and use that as an example. So a good example here, if I am elected, then I will lower taxes. So we have a conditional statement. Our P in this case is I am elected. Our Q is I will lower taxes. Both of these are either true or false, right? You either are elected or you're not. You either lower taxes or you don't. And these make up a conditional statement that we're going to use as an example. So we're going to go through and look at the truth values for P and Q. And we're going to look at this statement and we're going to ask ourselves, if I said this, would it be a lie? Okay? And this is a great example that sometimes it's easier to ask yourself whether something is false or not than it is to ask yourself whether something is true or not. And the cool thing about propositions is that they're either true or false. And if we can determine that something is not false, we can therefore say that it is true. So that's kind of the strategy, the technique we use for understanding the truth table a little better. It really has helped me looking at and asking myself, is this false or not? And determining that way rather than looking at if it's true or not. So hopefully this helps a little bit. So let's go ahead and go through this. P is true and Q is true. That means I was elected and I lowered taxes. It wasn't a lie, right? I clearly told the truth. I kept to my obligation. I kept to my promise, however you want to think of it. This is true, okay? So that's normally, students understand that one pretty well. So this next one, I was elected and I didn't lower taxes. Clearly it was a lie. I broke my promise. I didn't keep my obligation. People are upset, right? This is false. So these two rows, like I said, students don't have too hard of a time with. True, false. It's these last two rows, okay? What if the premise is false? So I didn't get elected. What does that mean? Well, that means I don't really have any obligation to keep, right? I don't have any promise to keep. No one has really expectations for me to lower taxes or not because I didn't get elected. I only said I would lower taxes under this condition, that if I was elected, I would lower taxes, right? So if I'm not elected, did I really lie whether I lowered taxes or not? I didn't lie in either case, right? It's not a lie. So both of these are actually true, right? And we kind of determine that by saying, well, these definitely aren't false, so therefore they must be true. That's the way I look at it, at least. Okay, so hopefully this helps. We have true, false, true, true. So really this conditional statement is only false when the premise is true and the conclusion is false. If the premise isn't true, we have no promise to keep, there's no obligation or expectation to do anything. And if the premise is true, then we have to keep to our conclusion. That has to be true as well. Otherwise, the whole statement is false, right? Hopefully this helps. Hopefully this makes sense. All right, so let's look at some conditional statements, which are all true. These are 3 conditional statements, and they're all true. And let's talk about what it means for a conditional statement to be true. Well, we just said a conditional statement is always true when the premise is false, right? When the premise is false, we don't care about the truth value of the conclusion. It's true in both those cases. So all we really need to show when we prove something like this is that when the premise is true, the conclusion is always true as well, right? If we can find even one example or one situation where the premise is true and the conclusion is false, the whole thing is false, okay? So for all of these 3 conditional statements, since they're true, anytime the premise is true, the conclusion is true as well. So if n is an even integer, then n squared is an even integer, always. All right, we can actually prove this. We'll do this as soon as we start doing direct proofs. This is a very easy thing to prove. If k is a number that's divisible by 4, then k is even. Pretty clear, right? Any number divisible by 4 is even, okay? So that means that there's never a number that's divisible by 4 that's not even. You can't find one, right? And if we have a premise that's not true, let's look even at this example. When n is odd, we don't care. We're not talking about when n is odd. We're just saying when n is even, okay? Then we have this last example. If f is a continuous function on the interval ab, then there exists p and q, real numbers, in ab, such that for each x in ab, f of p is less than or equal to f of x is less than or equal to f of q. This is actually extreme value theorem. This is a really important theorem, really important fact in mathematics that is of this form, a conditional statement, if then, right? And we even use this at the beginner level of calculus, all right? So there is stuff of this if then form, and when we have theorems like this, and we have proofs and facts like this, all it means is that if the premise is true, the conclusion is true. That's what it means for a whole conditional statement to be true. So hopefully that makes sense. All right, so if we start with a conditional statement, P implies Q, we can form new conditional statements using that premise as well as that conclusion, okay? So if we switch the position of the premise and the conclusion, and we say that the conclusion implies the premise, we call this new conditional statement the converse of P implies Q, all right? If we take the negation of the premise and we say that that implies the negation of the conclusion, then we have a new conditional statement that we call the inverse. If we take the negation of the conclusion and we say that that implies the negation of the premise, then we have a new conditional statement that we call the contrapositive of P implies Q. So let's go and look at the truth table for these. This may be a lot right now, but let's look at the truth table for these, and through that truth table, we're going to learn a new term called logical equivalence. All right, guys, so when two propositions have the same truth values in all cases, we say that they are logically equivalent, and we use this symbol. It's like an equal sign, but with an extra bar. We use this symbol to denote logical equivalence. So the reason I have logically here in parentheses is because this is the term I was taught. When I was taught this stuff, I was taught logically equivalent, but I referred to a textbook as well as some online resources, and it looks like they just use the word equivalent a lot. So maybe this logically part is optional, but I wanted to provide some context for why I'm saying logically equivalent, so I put it here in parentheses. So we say that two propositions are logically equivalent if they have the same truth values in all cases, and we've actually talked about one logical equivalence, even though we didn't explicitly state that's what it was. But remember when I said if a statement is true, that's the same as saying a statement is not false, right? It's the same as saying it's true. So that's kind of brings us to this equivalence here. A proposition is logically equivalent to the negation of that proposition. So let's consider all cases. Really, there's just two. The proposition is true or it's false. So if this proposition is true, then the negation of that proposition is false, and the negation of that is true. True equivalent to true, we're good to go in that case, all right? Second case, proposition is false. The negation of the proposition is true, the negation of that is false. False equivalent to false, we're good to go. So they have the same truth values in all cases, therefore, these propositions are logically equivalent. So this is actually a really good application of a truth table, is to prove this logical equivalence, because we can list out the cases and we can list out the truth values, and if they line up, then we can say that they are logically equivalent. So we're going to use this truth table to show that a conditional statement is logically equivalent to its contrapositive, and that the inverse of a conditional statement is logically equivalent to its converse. So this result is far more interesting and useful because this is something that directly relates to the conditional statement itself, right? This is an equivalence directly related to the conditional statement itself. So this is very useful. You will see this contrapositive a lot moving forward. This converse and inverse, you won't really see that much moving forward. It's not really that useful to us. But they each have their own name, converse, inverse. It's in a discrete math textbook, so I thought, you know what, I'll put it here. We'll get some extra practice with this truth tables, but probably not going to see it much moving forward. All right, so don't panic that this stuff is switched around in weird positions. We already know how to do this, so let's recap very quickly. I have my P column, Q column, and I went ahead and made negation columns as well. All I did was copy down the opposite value for the negation of each. And then I have my conditional statement here, true, false, true, true. We've already built this earlier, all right? So basically what I'm doing with each of these is I'm looking at my premise, and I'm going to look for the value of my premise, the truth value. And all I have to do is remember when this is true and when this is false. So again, quick recap. If my premise is true, then my conclusion has to be true in order for the statement to be true. If my premise is true and the conclusion is false, then the statement is false. If my premise is false, then we don't care what happens after that. True or false, doesn't matter. We say the statement itself is true. So using that same logic, we're basically going to treat this negation of Q as our P, as our premise, and this negation of P as our conclusion, and we're going to fill in this table, and we can do it pretty quickly using that method. So the negation of Q is false, therefore the statement is true. We don't even care what happens after that. All right, therefore the statement is true. Negation of Q is true, the conclusion is false, therefore false. This is the one case we have that makes a conditional statement false, true then false, okay? Next, we have a premise that is false. We can go ahead and write true. We don't even really care what happens after that. And then we have a premise that's true and a conclusion that's true, so we write true for that as well. So we have proven that in all cases, and this time there's 4 cases, they have the same truth values, right? True, false, true, true. Therefore, we have shown that a conditional statement is logically equivalent to its contrapositive. Let's go ahead and do the same for the inverse and converse. So our Q is kind of like our P in this case. It's our premise. So let's look for Q. We have true, true. So this statement is true because we have a premise and conclusion that are both true. Now we have a premise that's false, so we can go ahead and write true. We don't even care what happens after that. Now we have a premise that's true and a conclusion that's false. That's where we're false. That's our one case where we're false. And then we have a false premise, so we go ahead and write true. Now I'm going to do the same thing for this last conditional statement. Let's see. Negation of P implies negation of Q. Negation of P is false, therefore this whole thing is true. Negation of P is false, true again. Negation of P is true. Okay, so the premise is true, the conclusion is false. That's the case where we're false. And then lastly, the premise is true, the conclusion is true. Therefore, the whole statement itself is true. So we have shown that a converse and inverse of a conditional statement are logically equivalent. So hopefully this video helped. Hopefully it covered enough information for you to feel comfortable moving forward. Pretty soon I'll make a video on the direct proof method. We're going to do some direct proofs. Remember that if n is even, then n squared is even. We're going to prove stuff like that in a video coming up pretty soon. So stay tuned for that. Like, subscribe, leave comments below, do all that stuff. And most importantly, keep flexing those brain muscles. See you on the next video.